Okay, dear participants, welcome to 7th International Symposium on Multidisciplinary Studies and Innovative Technologies. In this session, we have a keynote speaker. Our keynote speaker is Associate Professor Muzaffer Kanan. Before starting his presentation, let me give you some biographical information about Dr. Kanan. Muzaffer Kanan is an associate professor of mechatronics engineering at Erciyes University, where he has been a member of the faculty since 2009. He obtained his bachelor's degree from Eastern Mediterranean University in 1994, Master of Science degree from the New Jersey Institute of Technology in 1996, and PhD degree from the Worcester Polytechnic Institute in 2008, all in electrical and computer engineering. From 1997 to 2008, he was with Raison Laboratories, Massachusetts, USA, where he was involved in various research and development projects in the area of wireless and fiber optic communications, resulting in 5 granted US patents with another 3 pending. His research interests are mainly in the areas of wireless capsule endoscopy, wearable technologies, and application of wireless communication technology for health and wellness. First of all, on behalf of organizing committee, I would like to thank you for your scientific contribution to the Congress. And if you are ready, you can share your screen and start the presentation.
Okay, thank you very much, Professor, for that nice introduction. Welcome, first of all. I'm very happy to address this Congress today on a very special occasion, actually, right on the eve of the centennial of the Turkish Republic, which will take place officially on Sunday. So what I hope to do over the next 20 minutes or so is to give you an overview. Let me share my screen really quickly here. Okay. Now, can everybody see my slides okay?
Yes, we can see. There's no problem.
Okay, great. Thank you very much. Okay, so what I hope to do over the next 20 minutes or so is to give you an overview of some of the work that we have been doing here at Erciyes University regarding something called capsule endoscopy, okay? And to kind of set the stage for what this is, I just want to kind of give you an overview of what we're going to be talking about. I'm going to spend some time, first of all, introducing capsule endoscopy and a recent variant of it, which we call robotic capsule endoscopy. And then we're going to talk about localization techniques, both for wireless capsule endoscopy as well as for robotic capsule endoscopy. And in this context, I would like to explicitly acknowledge 2 of my graduate students, without whose help and contributions this work would not have been possible. Namely, my PhD student, Memduh Suveran, who successfully defended his thesis last year, and will hopefully soon be an associate and an assistant professor at our department, as well as Mohamed Chil, who completed his master's degree. So to kind of set the stage for this, capsule endoscopy is something that actually focuses on, is a medical imaging technique that focuses in on a section of the human anatomy known as the gastrointestinal or GI tract, which is a medical term for that part of the human anatomy that specifically focuses on ingestion, digestion, processing, as well as the waste excretion of all of the the food that we ingest as humans, and basically consists of 5 main or rather 4 main sections: the esophagus, the stomach, the colon, and the small intestine. And capsule endoscopy is basically is a new generation medical imaging technique that focuses on imaging of this part of the human anatomy. Now, the reason, of course, that capsule endoscopy has been a necessity, of course, is that there has been a lot of cases of diseases. There are lots of cases of diseases of the GI tract, including cancers. And the images that you see here are actual endoscopy, are actual images from different sections of the GI tract that focus in on various different kinds of anomalies, such as bleeding or polyps, which may or may not be cancerous, of course. But the GI tract also happens to be a place in the human body where a lot of cancers happen, actually. And this data here. This is the latest available data that was available from the Global Cancer Observatory. And you can see here that about over 20% of the cancers, of all of the cancer cases observed worldwide, actually come in from the GI tract, which is sizable, okay? Now, the way to diagnose these different illnesses of the GI tract, the traditional method is something called endoscopy. Now, since we're not face to face, I'm not in a position to know how many people here know what endoscopy is. So I have taken the liberty of assuming that people don't know exactly what endoscopy is. So I'm just going to spend a few minutes just kind of going over traditional endoscopy. What an endoscope is basically is a long plastic tube through which runs generally a section of fiber optic cable with a camera at the end. And this long plastic tube is basically shoved down either the patient's throat or the rear end via the anal region, and is used to visually inspect a part of the body, mainly the gastrointestinal tract. Now, if you've ever gone through this procedure, an endoscopy procedure, you will know that this is something, or if you have friends or family who has, obviously, you will know that this procedure can be excruciatingly painful, to the point where most of the time patients have to be sedated in order to go through this procedure, to the point where a lot of people actually don't want to do it. And it has, of course, various different kinds of variants, such as gastroscopy, which focuses more on the stomach and the region around the stomach, the esophagus and the duodenum, and colonoscopy, which focuses on the large intestine. Now, wireless capsule endoscopy, which is a technology that has come about in the last, I want to say, 15 to 20 years, actually was a revolutionary technique in the sense that it actually avoided a large part of the discomfort associated with traditional endoscopy techniques. And what a wireless capsule endoscope is basically a miniature pill-sized camera that the patient swallows just like an ordinary pill. And this pill, the graphic of it you see here in this slide, actually incorporates a small camera, and it also includes a small wireless transceiver, which takes the pictures taken by the camera and relays it to an on-body receiver. Now, the main purpose of this initially was to examine the small intestine, which was, due to its location and its convoluted nature, not something that could be easily imaged with traditional endoscopy. But over time, of course, the functionality expanded to include the entire GI tract. So the way capsule endoscopy works is that the patient swallows the capsule. The capsule travels down the different sections of the GI tract, taking images and relaying them to an on-body antenna and transceiver system, which is shown here with a strap-on kind of antenna arrangement. And the data, which is recorded here in this device here, is then reviewed offline by a medical specialist, a gastroenterologist to be more precise, in order to diagnose different kinds of diseases. So the kinds of WCE systems are really twofold. One, which is called passive wireless capsule endoscopy, which is really the kind of capsule endoscope that is used widely in clinical practice today. This is the kind that the patient generally swallows, and the pill-sized capsule basically travels through the GI tract mainly via the natural forces of peristalsis, the natural muscle contractions all along the path of the GI tract, and then naturally, of course, excreted out of the body. But the real and the exciting development in the capsule endoscopy space is what is known as active wireless capsule endoscope, also known as a robotic capsule endoscope, which is really the focus of this presentation. Now, regardless of whether you're talking about an active or a passive capsule endoscope, though, all these systems have what is known as the localization problem. Namely, when the capsule takes an image, okay, and this is one example. This actually shows a polyp, which may or may not be cancerous, actually. It is very important for any, for the planning purposes of any potential surgical intervention or a biopsy procedure to know exactly where this anomalous, abnormal condition really resides. Okay, so what you have to be able to do is to be able to correlate each endoscopy image with a location within the GI tract, and that gives rise to the localization problem. Now, when you're talking about a robotic capsule endoscope or an active capsule endoscope, by that, of course, we mean a device which then becomes a small-scale robot. So it's no longer, we're not talking about an endoscopy capsule that just goes through passively via the body, but just it can be externally controlled via like a joystick-like arrangement. So the specialist can basically control the capsule at will, take more detailed imaging data, or maybe even a biopsy sample in the area of interest, and then they can just basically do all these different kinds of things that can potentially give rise to even non-invasive treatment. Okay, now, but even in this case, in fact, for the robotic capsule endoscopy case, the localization problem becomes even more critical, because in order to be able to effectively maneuver the capsule, the specialist needs to know exactly where in the GI tract the capsule is. And there have been some new developments in the robotic capsule endoscopy space. In fact, this graphic on the right is in the marketplace called Navicam. It's manufactured by this a US-based company called ANX Robotica. And I was actually browsing through their website yesterday to see if there was any interesting information I could get for the purposes of this presentation. And oddly enough, they talk a lot about the remote maneuverability of the capsule, but they do not talk about the localization, which I find kind of interesting. But anyway, now, specifically, though, regarding the robotic capsule endoscopy case, though, since the doctor has to be able to maneuver the capsule in real time and have to know exactly where the capsule is at any point, there's also a real-time performance requirement that comes in. So not only do you have to satisfy an accuracy requirement, but you also have to satisfy the real-time performance requirements, which of course is, puts the problem in a totally different dimension. Now, so how do you localize a capsule inside the human body? Well, there are different kinds of techniques that you could really use, existing techniques in the literature. One that involves computer tomography. You can use X-ray imaging, both of which, of course, are potentially harmful to the patient because they use ionizing radiation. Of course, the patient is exposed to potentially undesired levels of ionizing radiation. You could use magnetic resonance imaging, which, of course, tends to be cumbersome. I mean, you're looking at this very big piece of equipment that you have to use for this purpose. 3D ultrasound, which of course has certain issues of its own, particularly with regards to accuracy. Radio frequency is more of an opportunistic type of localization technique, which for the most part attempts to leverage the wireless signal that the capsule already emanates emits, I should say, for the purposes of localization. And of course, image processing. In other words, looking at the images and trying to deduce from the sequence of images exactly where in the GI tract the capsule is. Now, the issue here is that none of these techniques actually provides the required amounts of accuracy for clinical use. And so many of the techniques that have been proposed in the literature actually incorporate a hybrid combination of these two techniques. Specifically, we're seeing a lot of works in recent years, specifically on the hybrid combination of these two, the RF as well as the image processing. But of course, the disadvantage of that is that it makes the algorithms overtly complex and potentially unusable for real-time use. So what we have been focusing on for the purposes of our research is magnetic localization. Now, magnetic localization basically involves measuring the magnetic field that the capsule creates around it as it travels through the GI tract, and uses that information to localize the capsule. Now, one really significant advantage of the magnetic localization technique is that as far as static and low, at least the static and low frequency magnetic fields are concerned, the human body is the same as free space. So the human body tissues have no impact on the magnetic field that have been generated, unless, of course, you're talking about the distance-dependent attenuation of the magnetic field, which, of course, is of course a reality anywhere. But as opposed to techniques like RF localization, which uses an electromagnetic field, really, of the RF signal, which, of course, are affected, at least the electric part, are affected to different degrees by different human body tissues. That doesn't happen to be the case with magnetic localization. So the bottom line is that high accuracy localization on a real-time, on a near real-time basis is possible, which of course makes it a perfect solution for the robotic capsule endoscopy case. So we have been spending quite a bit of time regarding exploration of the different magnetic localization alternatives for RCE. So the first focus of our work really has been to optimize real-time magnetic localization performance for RCE. And basically, the fundamental idea here is that since the human body is magnetically the same as free space, as I mentioned earlier, the problem of magnetic localization really boils down to localizing a magnetic field source in free space, given measurements of the magnetic flux density. And this magnetic flux density can be analytically modeled given a magnetic geometry. And you can compare the results against the data that you get from the magnetic field sensors. And the location and the orientation values is the one which minimizes the error between the magnetic flux density and the values obtained from the analytical model. So we're talking about mathematically a six-dimensional problem. The three parameters for the location, the x, y, and z, and the three for the orientation angles, namely the alpha, beta, and gamma, which are widely known in the literature as the Euler angles. So now, in order to get things started here, you need models for magnetic flux. And there are several different ways in the literature of obtaining this analytical model for the magnetic flux. One of which is what's called the current model, which, if you are familiar with the fundamentals of electromagnetic theory, the magnet is treated as a current source, and the magnetic flux density is then calculated on that basis. Now, what we have done in our case is to focus on a cylindrical magnet geometry, which allows easy integration onto an existing capsule. And all the derivations then can be performed in cylindrical coordinates. One significant disadvantage of the current model is that mathematically it turns out to be very complex, which of course has an impact on computational time and therefore suitability for real-time use. So other models, such as the dipole model, are often preferred. Now, the dipole model is used to express the magnetic field distribution of the magnet and to determine its position in free space. And with the magnetic dipole model, you can calculate the magnetic flux density of the magnet. And these are the required set of equations that you can get on that basis with these parameters. I'm not going to go through the different details of these equations, So in order to quantify the performance of magnetic localization techniques for RCE, you need, first of all, a framework for the performance evaluation. And of course, one very important part of this involves an experimental system, with the details of which I will share in a few minutes. But this experimental system includes an array of magnetic sensors which measure the magnetic flux density of the capsule, which has a magnet attached to it. And these sensor measurements are compared against the magnetic flux density model, which of course allows you an analytical calculation of the magnetic flux density based on the magnetic geometry. Now, there is an error, obviously. The sensor measurements won't match the flux density model precisely, owing to several factors, most significant of which, of course, is sensor noise. And of course, there will be an error associated with the comparison between the sensor measurement and the model. Now, the idea here is to find the values of the orientation and location parameters that minimizes this error epsilon. And you can do that through the different kinds of optimization algorithms, which include different kinds of meta-heuristics algorithms, which I will talk about next. And of course, iterative algorithms, a good example of which is the Lemmenberg-Marquardt algorithm. And based on that, you can calculate, if you know the real location of the capsule, which in an experimental system you can easily estimate. You can calculate the localization and orientation errors. Now, meta-heuristics algorithms, this is generally well known, general class of algorithms which attempt to solve optimization problems in a biologically inspired manner, usually based on modeling different kinds of phenomena, such as behaviors of different swarms of different kinds of biological organisms, such as schools of fish or even swarms of bees. And what we have used for the purposes of this algorithm involve 4 algorithms: PSO, TLBO, DE, as well as the ABC or artificial bee colony algorithm. So the experimental system that we have includes the array of magnetic sensors, which measure the magnetic flux density, as I mentioned, and you have the intestinal model, which we have designed and generated with a 3D printer, through which the capsule moves, and this is what the capsule looks like, basically, with a series of permanent magnets attached to it. And when these values of the magnetic flux density are relayed via this microcontroller to the PC, to a computer, then the computer then takes over, computes the location and the orientation parameters. And what I will do next, I'm just going to show you a quick
Dr. Khan, can you hear me? I guess connection is lost. We will wait him to come back. Are you here, Dr.
Yes,
Khan?
I am. I dropped off for one moment. I don't know why. Can you still hear me?
Yes, we can hear you, but
Okay.
you need to share your screen again.
Yeah, I will. Okay. I guess you have caught the last part where I was talking about the experimental system, right? So
Yes.
I'll just pick it up from there. I'm just going to show you a quick video of the system in action. Okay, can you all see the video right now?
Yes, we can see.
Okay, all right. So let me. I'm not going to play the whole part of the video, just a certain section of it. Okay, so what you can see here is that on the screen, as the capsule moves through the experimental system, its location and orientation parameters are calculated in the background and displayed on the screen. So what we have done here is to model a sort of a clinical scenario where, as the capsule moves, the doctor can follow the location of the capsule and control it approximately. Okay. So this is basically what the system essentially looks like, okay, and how it operates. Okay. I think I'm just going to stop the video here for now, and I will go back to my presentation really quickly. Stop sharing. Okay. So back to the presentation. So what we have done here, what we're showing is the actual amount of errors that we get out of the system. And I don't know if you can see in front of you, but there's a red line here which actually shows the real path that the capsule is supposed to follow. And on top of which, on top of this real path in red, we have superimposed the errors that we have calculated as a capsule was moving, and we were calculating its location and orientation parameters. So we can see that the maximum amount of the localization error is roughly in the neighborhood of about 8 to 9 millimeters. And the main reason for that is the sheer distance of the capsule at certain locations from the array of sensors. And but for the most part, we are seeing errors, generally in the region of 2 to 3 millimeters, which is actually a pretty good performance. And we're doing this on a real-time basis as well. So here's another view of the results, where we see that generally 10 millimeters is the maximum amount of error that we get at only one location, but generally on average we get about 2.5 millimeter localization error and about 3.5 degrees for the orientation error. What's even more important though is that is the average computational time, which currently stands at about 137 seconds. There are ways, of course, to optimize that even further, which gives rise to about 7 Hertz refresh rate. So we can calculate about 7 location estimates every second, which of course can be considered acceptable for the real-time requirements for RCE, considering the fact that we really don't expect the capsule to move very fast inside the body. So so now I'm going to shift gears and talk a little bit about the analysis of fundamental performance bounds. So the focus here was a lot more practical. So we're going to shift gears and talk a little bit more about the practical of the theoretical aspects of performance analysis. And for the purposes of this analysis, performance analysis, we use something called the Kramer-Rao lower bound, which is a popular method that is used in practice for predicting performance and for parameter estimation. And it is generally well known as a lower bound for unbiased estimator performance. When we say lower bound for estimator performance, we're talking about a lower bound for the estimation error, basically. So basically, it gives you the best performance that is available in a given scenario for an unbiased estimator. Now, the way in which we calculate the CRLB is by computing what is called the Fisher matrix, which of course is the log likelihood, which is computed by taking the second derivative of the log likelihood function of the observations given the errors epsilon. And then you go through the procedures, take the inverse of the matrix, and that gives you the CRLB. So what we have done is to compute values of the CRLB for magnetic localization in RCE, considering the magnetic flux density expression given by the dipole model, and then use that to analyze exactly how the CRLB behaves in different kinds of scenarios. So that's really what we're going to be talking about over this section of the presentation. These are the expressions for the dipole model, and then based on that, you can calculate the values of the Fisher matrix, and then take its inverse and get some results. So what we have done was a cylindrical magnet sort of arrangement with a sensor that was roughly modeled on the Honeywell 3-axis magnetic tensor with a sensor array, and the performance criteria, which was the diagonal of the CRLB, which gives you a lower bound on the root mean square error, actually. So increasing the number of sensors is the first kind of study that we have performed. And we have found, of course, that as we increase the number of sensors, the CRLB goes down. So in other words, the best achievable performance then gets better is really what this means. As far as the localization error is concerned. We're focusing on the localization error here. But we find that as we go beyond a certain value, the performance really doesn't get any better. So increasing the values of the number of sensors beyond a certain value, roughly in the neighborhood of about 30 to 32, doesn't really get you all that much improvement in performance, which of course has got implications for system costs, especially. We have also modeled several different cases of how the capsule motion in the GI tract affects the CRLB. So we're talking about the motion along the z-axis here. And these are the results that we get. As we, of course, get further and further, the CRLB, of course, goes up, which means that the performance gets worse. But of course, one other important thing is that given that if you are within a certain distance away from the capsule, it really does not matter which or how many sensors you use, because the signal to noise ratio presumably will be high enough anyway, so your performance will be assured. Now we're going to focus on a more complex kind of motion where the capsule moves in both the X and the Y plane, okay, which is another potential kind of location, but without any change in the orientation vector. And what we observe here is that the CRLB, gets worse as we, move away from the origin value, but gets closer as we get closer to the origin section. Now, changes in orientation, of course, are a reality. So we have explored the change in orientation as a capsule moves in this circular kind of motion. And these are the values that we get as a result of this kind of motion, as a function, of course, of the number of sensors. So in summary, we can say that high accuracy, real-time localization of a robotic capsule endoscope device inside the body is possible. And we have the results that we have definitely show this feasibility, and the result will pave the way for a new generation of medical imaging, diagnosis, and treatment platforms. So thank you very much for listening. That's all I have to say. If you have any questions, I'll take them now.
Dr. Kanan, thank you very much for this great presentation. Dear participants, do you have any questions about this topic? As I can see, there are no questions. Once again, I would like to thank you very much for your contribution to the Congress. And now I'm ending this session. Thank you.
Okay. Thank you very much.